Alright, now we've got an additional video for more solving with logarithms. I believe this is up to the fourth video for this, so you'll have a lot of examples that you can have in these videos, so I hope this is helping. So problem 8 here, e to the 2x equals, for my students by the way, this is 8 on your lesson 4 homework from the logarithm unit. So e to the 2x equals 3 pi to the x plus 1. So I've got an exponential equation. I have these variables, an x over here and an x over here, that I need to solve for. They're in the exponent location. So I ask myself, can I set like bases and solve using my exponent rules? Well, base e there, base 3 pi there. So no, that's not a good idea to try to set like bases. So what I need to do is take the logarithm of both sides. I am going, because I have a base of e right here, I'm going to take the natural logarithm of both sides. So ln of e to the 2x is equal to ln of 3 pi all to the x plus 1 power. Okay, ln of e is actually that logarithm theorem that says when the base of the logarithm, which is base e, and the base for your exponent are the same, you're only left with the exponent part. So I'm going to work this off to the side. We haven't applied this in a while, so I want you to see what it is. So equals, I'm going to make this equal y here. So instead of ln, I've written this as log base e. ln is log base e. We've used that quite a bit in this unit, so you should know that by now. So when we ask ourselves, well, what is this whole thing equal to? Well, this is that special property. I might have said theorem before. Technically, this is a property of logarithms. So e to what power? So e to what power is equal to e to the 2x. Well, both of these are base e, so that means y has to be 2x. So in other words, this answer, log base e of e to the 2x, is actually just equal to this 2x part. So it's just equal to the exponent. So I can simplify this by marking that out, and now I have this. 2x equals ln of 3 pi to the x plus 1 power. So now I can apply that all-important logarithm theorem that says I can pull an exponent up front as a multiplier, and that's what I'm going to do next. So now I have left side 2x, didn't change, and now I have the x plus 1 quantity times ln of 3 pi. So I need to put that in parentheses there. So ln of 3 pi is just some value, it's a quantity, so I can now distribute. So I'm going to do that here, distribute. So I get on the left side 2x still, and then I get x ln of 3 pi, the argument of that logarithm is 3 pi, plus ln of 3 pi. So that's just distributing here. ln of 3 pi times x is this. ln of 3 pi times this one is just itself, ln of 3 pi. So now I need to isolate all of my x's, so I'm going to subtract this whole term to the other side. Before I did the shorthand on a previous problem in another video, so I'll actually write it out here so that you can make sure you're clear on what we're doing. So that cancels. And now I have, I'm going to rearrange a little bit, but I have this 2x minus x ln of 3 pi is equal to ln of 3 pi. So now I can, if you notice, we have an x in both of these terms, and when you're solving and you have a situation like that, you want to factor that out. So coming up here, I'm going to factor out that x, and I'm left with 2 minus ln of 3 pi, and that is equal to ln of 3 pi. Put that parentheses around the argument there. So all we did is we factored out this x and this x. That's all we did. And if you distribute this back in, you would end right back here where we started in the previous step. So we know that we did our factoring correctly. So now we are going to simply divide by this 2 minus ln of 3 pi quantity. Cancels here. Do the same thing over here, and we'll actually be done. So final answer is x is equal to ln 3 pi in the numerator, all divided by 2 minus ln of 3 pi. And that is some quantity, it's some decimal value. We don't have a calculator, so we're going to leave it like this. The main thing is we have isolated x. Now, don't make the mistake of trying to cancel this with this. You can't do that because of this subtraction sign down here. So don't do that. This is your full answer. All right, let's look at an additional example here. Okay, number 9 on the homework for my students and an example for anyone else. We have 12 equals 2e to the x subtract 10. So we have this variable locked up here in this exponent location. So the first thing I'm going to do is simply add the 10 to both sides here. And we'll end with 22 equals 2e to the x. Then I'm going to divide by 2, and I get 11 equals e to the x. So now I have a standard, pretty straightforward exponential equation. So I ask myself, technically 11 is raised to the first power. So I ask myself, can I make e and 11 match up with the same base to solve this? Well, no, I can't. So then this is an application for taking the logarithm of both sides. So I have a base of e here, so usually it's appropriate when you have that to go ahead and use the natural logarithm. Take the natural logarithm of both sides, and you'll see why in a second. And if you haven't already figured out this pattern, so ln of 11 equals ln of e to the x. Well, then whenever we have this property, natural logarithm has a base of e, this exponent has a base of e, so when those match, our property says that we can mark those out and we're only left with the exponent. So I'm going to do that here. So ln of 11 is equal to x, and we're actually finished with that problem. So x equals ln of 11. I'm going to show you this again, why this is just equal to x. So ln, same thing as log base e. So we have this. Ln of e to the x is the same thing as log base e of e to the x. So we ask ourselves, well, why is this equal to x? Well, here's why. If I set this thing equal to y, apply the loop rule. So e to the y, the definition of a logarithm is described by this loop rule. So e to the y has to equal e to the x. Well, both of these bases are the same, so that means that y has to be x. So this right here is the same thing as x. So in the end, we're only left with whatever is in that exponent location. So I've shown you that a few times. It's at this point you just need to recognize this and immediately just cross it out and just realize you're only left with the exponent part. Okay, so that is it for number 9. We'll work one more in this video and call it good. Alright, last one for this video. I chose this problem because it has an absolute value. And you probably haven't looked at an equation with absolute value in a while, so I thought this would be one that you might have questions on. So all I'm going to do here is apply the loop rule to solve this one. So 2 to the third power is equal to the argument of the logarithm, the absolute value of x plus x, x plus 6. So now I have 2 cubed is 8, so 8 is equal to the absolute value of x plus 6. When you are solving absolute value equations, you may recall from Algebra 2 that you end up having to solve, once you get it to this step right here, you actually have to solve 2 equations. So that says that x plus 6 has to be 8, or x plus 6 is negative 8. So we have to solve both of these. So when you have the absolute value, you have to solve a negative 8, whatever's here, you solve it for whatever is here plus the opposite sign of that. So we're solving for 8 and negative 8. So subtract 6, x equals 2. That's one answer, one possible answer. And subtract 6, and we get x equals negative 14. So we have 2 answers on that one, 2 and negative 14. Alright, I'm going to go back and work one more. This video is not quite 10 minutes, so one more. Alright, last one for this video, number 14 here. I see an opportunity to work this 2 different ways, one of which I think is easier than the other, so I thought I would show you both. So notice we have the natural logarithm with an argument that has a base of e in actually every single case. Base e for the exponent there, base e for the exponent there. So we actually have that property that I've shown you more than once that says if you have ln of e, you're only going to be left with whatever is in that exponent location. So first thing, that's what I'm going to do. So this part is just equal to the exponent x. Equals this part is just equal to the exponent 4 plus this part is just equal to the exponent 3 with a 2 multiplied in front. So plus 2, the quantity 2 times 3. So x equals 4 plus 6. So x equals 10. Done. That one is 10. That is the answer. So, and I think that's the fastest and cleanest way to do it. Another way to do it is you can apply the theorem that says a multiplier in the front can be brought up as an exponent. And I'll show you that. So we have ln of e to the x is equal to ln of e to the 4th power plus ln of e cubed, and then we brought this exponent up as a 2. This came up as an exponent of 2. So outside to inside we multiply. So ln of e to the x equals ln of e to the 4th power plus ln e to the 6th. And now we have ln of e to the x is equal to ln of e to the 10th. Whoops. That's not right. We're going to apply, it is going to be the 10th, but let me explain why. So remember the logarithm rule that says you can combine when you're adding logarithms with like bases, you can actually end up combining them through multiplication. So this is the same thing as ln of e to the 4th times e to the 6th. Okay, we're just combining the arguments of each of those logarithms through multiplication, and that gives you, I just skipped a step when I said ln of e to the 10th earlier. So that is what it is, but I wanted to show you why. So you add these exponents, you get ln of e to the 10th, and then you simply mark out the ln of e part, and you're just left with the exponent, so x equals 10. So that's a little bit longer, probably a little bit more confusing than this one, but I just wanted to show you that you can work it more than one way. Okay, that's it for this video, and that's it for this lesson.